Let's just do a quick preview before the last lecture of before proceeding ahead. The last topics covered in the last lecture, we discussed about the very famous PCR reaction. PCR is polymerase chain reaction. It's essentially a DNA amplification technique which is done in vitro by the use of an enzyme and some of these other different reactants like oligonucleotides, different primers. Then essentially this reaction takes place under a certain pH condition. We also talked about real time PCR, which is essentially a snapshot by snapshot view of how the amplification reaction proceeds. It's essentially done by using fluorescence readout methods, wherein some fluorescence dyes are used to either intercalate or are used or are paired with some other dye molecule or some quencher molecule in a manner that when the reaction proceeds, the distance between the primary fluorophore and the secondary fluorophore or the quencher changes, as a result of which there is an increase in fluorescence, and you can detect whether successfully the reaction is being carried out or not. So real time PCR really gives you an idea of what is the current amplification rate of a certain strand of DNA molecule as the reaction proceeds. So we also tried to design PCR microreactors. PCR, again, because of the rapid thermal cycling issue associated with the process, can be very easily translated onto a microchip level, and there are a lot of benefits to do such a react, one of them being rapidity, because essentially you are using or you are trying to heat up a very little mass of fluid in such a microchip architecture by going into a thin surface film. Okay, so you are spreading out a volume or a bulk into a thin surface film, and essentially you are using the surface area for promoting higher heat transfer rates, and thus quicken the ramp up and ramp down times, so that the overall cycle time can get reduced because of that. And the PCR reaction happens much more quicker in the microreactor mode. Okay, so we talked about developing an RC modeling where we took thermal capacitance, thermal resistance, and try to see by deriving an analogy between the electrical parameters like voltage with physical parameters like temperature, which drives the process. We also looked at how the charge in an electrical circuit can be kind of equalized to or made equivalent to the heat flow in a thermal circuit, and then try to develop the time constant from that circuit point of view. So essentially at the end of the day, the take home message that we had is that really the ramp up ramp down time is independent of the reactor volume, especially at these scales, and there is a certain finite time constant which has to be used or spent in order for the reactor to get to a certain level of temperature that's equal to 3 times of RC or 3 times of the time constant value. So we tried these numerical approaches on one PCR reactor design example. We will do some more today and then move on to our next topic, wherein we will study a little bit more about how this DNA polymerase within a cell tries to replicate DNA molecules. Okay, so let's do another example on designing a whole PCR process by using this time constant. So in this particular example, we want to find out the total time required for sample preparation of this in this DNA assay. Okay, not sample preparation really, for the whole assay to get completed. So we assume the constants from the earlier example, wherein we already found out that the time constant for the process was about 0.28 seconds. Okay, and essentially using the reactor design fundamentals, we found out that the total time that it would take for the temperature to hit the 90% mark would be about 3 times such time constant, which is 0.84 seconds. Okay, here we assume the extension time again from the earlier examples, wherein we assume that 1000 base pair DNA was really the template DNA. The extension rate of the enzyme was about 50 base pairs per second, which makes the extension time, the longest time step, about 20 seconds. We further assume the denaturing and the annealing times to be 5 seconds each, and in this case we want to find out the total time needed for the PCR assay. Okay, so let's try solving this problem by assuming a certain time constant of 0.28 as had been indicated before. Okay. In this particular case again the total time which the total cycle of the PCR could be represented by 3 temperature steps here. Here you go from, let us say, about 25 degrees Celsius all the way to about 90 degrees Celsius, stay here for a little bit, go down to about 54 degrees Celsius, stay here for a little bit, and then again go up all the way to about 72 degrees Celsius. Okay. So in one cycle really you are doing this heating cooling mechanism thrice. Okay. This is the first time you are doing the ramp up, then essentially you are ramping down, and then again you are ramping up to all the way to about 72 degrees Celsius. So as we know from our last illustration that this ramp up and ramp down time is really independent of the 2 temperature states between which it should take place, between which it happens. So it is essentially dependent on the reactor volume. In this particular case the 3RC or the 3 time constant was found out to be 0.84 seconds, and in a whole PCR cycle you are seeing that this time constant has to be executed 3 times because there is essentially 2 heating and 1 cooling steps. Okay. So there is 1 heating here, 1 cooling, and then there is another heating up here. So it gets repeated 3 times, this time constant, plus you have the independent, the extension, annealing and denaturing step. So you have T denaturing, T annealing plus T extension. So this essentially is a very important concept to understand. Okay. I would just like to point your attention to this fantastic problem wherein it's really independent of the temperature, in between which this body or this reactor is oscillating, irrespective of whatever the 2 temperature points are. So in this case, for instance, you see that you have to go in one instance from 25 degrees to about 90 degrees Celsius, and then you have to come down from 90 to 54 and from 54 back to 72. So really the delta T is varying in this case, but we assume that the time constant, the amount of time that it would take for the fluid or the particular volume of fluid inside, okay, inside the chamber to reach the temperature of the walls of the chamber would essentially be constant. Okay. It will depend just on the properties of the thermal mass. Now if you are to assume that there is a surface where we can rapidly change the temperatures without really having to for the temperature of the surface on which this reactor is placed to reach the particular temperature point. So in that case the only time that is needed, assuming the temperature of 90 is just about met, or the temperature of 72 is just about met, the only time needed is to heat up the bulk, which again is constant. It is not a function of the 2 temperature states, but just the volume to area ratio, which determines in fact the time constant in that particular case. So really if you can have a control on the ramp up ramp down of the material that is involved in the heating process, like for example the remaining portion of the chip over which probably the heaters are placed, then controlling from the surface which is in close proximity to the solution is really independent of the 2 temperature states. This is a very important concept to be understood at this stage. Okay. So in microchip architectures, the advantage which such architectures provide is really the fact that such a surface, okay, which is essentially the surface wall holding the bulk or holding the fluid, that surface is essentially very small. It has its own thermal mass which is effectively very small, and so therefore it can rapidly reach a certain temperature point from another point, whether it is cooling or heating. Also because the surface area is more prominent, it happens rapidly, and so this issue is of extreme importance. Then once this temperature is reached, we don't need to bother about what is going on in terms of heat transfer within the bulk of the particular solution. So you have this the total time of the reaction in this case as 3 times of 0.84 seconds, which is the time constant for essentially for the PCR volume or for the microreactor volume from the last question, and plus denaturing time plus annealing time plus hybridization or extension time. Okay. So we already know that the annealing and the denaturing times are all 5 seconds as illustrated in the question itself. From the earlier example where we calculated 1000 base pair DNA, an extension rate of about 50 base pairs per second, we found out the total time of hybridization is about 20 seconds. So this is 20 seconds, and therefore the total time that one cycle would need really is about 32 seconds in this case. Okay. And if you were to assume that you had to produce 10 to the power 5 copies per mil from about 100 copies per mil of the particular solution, then so assuming that about 10 cycles would be needed to do this, you will be left with about 325 odd seconds for, by the by, this is actually 32.5, this is about 2.52. Okay. So 32.5 here, so it's about 325 seconds that you would take for cycling this for about 10 times, so that you could produce about 10 to the power 5 copies of DNA from 100, assuming the efficiencies that we had discussed in the last lecture, in the last example. Okay. So your total time for the whole reaction to have 10 to the power 5 copies per mil starting with about 100 copies per mil is about 325 seconds, or about 5 minutes and 25 seconds. In a macro scale reactor, thermal cycler where there is a huge aluminum block, this would go as high as about close to 2 to 3 hours. Okay. So there is definitely an advantage that microscale PCR has to offer. So after this designing problems are over, let us try to understand this process of DNA polymerization, which is extremely important process for understanding of the basic kinetics or kinematics of the way that DNA is reconstructed between cells, okay, as they split and get reconstructed. So essentially, if we look at the DNA structure again and closely evaluate it, the way that the sugar phosphate backbone is being laid out is really opposite to each other. Here in this particular illustration, as you can see, shows how, if you look at this particular side, let's say this side, the sugar phosphate or the sugar bone or the sugar molecule is really pointing from the 3' to 5' side. If you may remember from our earlier discussed nomenclature for DNA molecule, this is the 3rd carbon, it is called 3', this is the 5th carbon of the sugar, it is called 5'. So this direction is from 3' to 5'. Very amazingly, the other strand of the DNA has an opposite direction of the sugar molecule. So it's starting from the 5' end, okay, and going up to, let's say, the 3' end of the earlier strand. Okay. So as you see here, this sugar molecule, the 5' is pointing downwards, as opposed to this where the 5' is pointing upwards. So the two strands of DNA really are just opposite to each other in terms of the way that sugar molecule is aligned or oriented. It's a very interesting phenomena, because that kind of defines the way also the DNA polymerase is able to replicate these moieties, independent moieties, especially when within cells. So initially, the simplest mechanism of DNA replication seem to be continuous growth of both strands or daughter strands from the DNA fork. So this right here is the DNA molecule, as you can see here, and if you see this closely, there is a zip, there is an unzipping action. Okay. there is an unzipping action here, and there is an opening of these two strands in both directions like this, and therefore thereafter there is a continuous growth of both the new strands from the DNA fork. Okay. So essentially people used to think that when these two daughter strands have been isolated, one in this direction, one in this other direction, they would automatically replicate from the moieties which are present in the solution, that is the triphosphates and the kind of DNTPs or triphosphates and the enzymes which do the suturement. Okay. So people used to think that as the fork is being separated and as the new daughter strands generate, the suturement kind of happens parallelly, and therefore you get this red train here, or this red portion of the molecule is the sutured portion. Okay. This is the artificially sutured portion. So just because the DNA molecule has a base which is antiparallel to each other, and just you saw just in the last point discussed. So just because the orientation of the DNA has one sugar pointing from 5 prime to 3 prime on one flank, another sugar molecule pointing from 3 prime to 5 prime on another flank, they can be said that they are antiparallel. So therefore there really needs to be a growth for these daughter strands which are emanating out here. Okay. So in the antiparallel direction, so this is, let us say, daughter strand 1, this is daughter strand 2, they are emanating and getting unzipped and getting reconstructed, and the red portion is the reconstruction on the particular strand on both ends. But in that case just for the sake of maintaining the antiparallel nature, one of the suturements should be starting from 5 prime to 3 prime, which is opposite to this 3 prime to 5 prime, this is antiparallel to this other flank 3 prime to 5 prime. Another should be from 3 prime to 5 prime, which is antiparallel to the flank 5 prime to 3 prime. Okay. So this concept needs to be a little more clear. So just because the two strands on the DNA on both sides, or two flanks on both sides, are antiparallel in nature, it automatically means that the suturement should be from 5 prime to 3 prime on one side and from 3 prime to 5 prime on another side. Okay. Now effectively this would need two different enzymes, but in nature if you look at what really does the job, there is only a single type of enzyme which does this job. So then effectively there should not be any stitching in one of the directions. So here the need would be really of two different enzymes, one would stitch from the 5 prime to 3 prime, another would start stitching from the 3 prime to 5 prime direction, but only one enzyme has been isolated so far in nature, which can only do the suturement from the 5 prime end of the DNA molecule to the 3 prime end of the molecule. So therefore there has to be a mechanism which can accommodate this very fact that the presence of only a single enzyme would also let the strands grow in a manner that is well suited, and still it develops this antiparallel nature or characteristics. So in the late 1960s researchers for the first time studied this by labeling DNA of a dividing bacterial cell with this radioactive dye H thymidine. Okay. And this labeling was essentially used to ascertain what is going on, especially along the 3 prime to 5 prime direction. We already know that the enzyme that exists in nature does a suturement only from the 5 prime to 3 prime direction. So this labeling was done in a way that only the most recently labeled DNA or replicated DNA behind the replication fork became suddenly radio labeled. Okay. So you have a fork, let us say, and it is opening up like this, and if I somehow am able to label this particular DNA behind this replication fork, that means if this is the fork which is opening, this is behind it, that means this parent DNA which is able to split up into two, if I can suddenly label it, radio label it, I have an idea of what is going on. Okay. How this label changes from one parent DNA to the daughter DNA. So from all this we do have information, or we have some very good idea about what is going on, particularly in the 3' to 5' direction. So scientists find out that in the 3' to 5' direction, it is really small fragments of about 1000 to 2000 base pairs which get first separately made in the 5' to 3' direction, and then the suturement really happens in the 5' to 3' direction of these groups or fragments, not single base pair by single base pair as normally happens in the 5' to 3' direction. Let me just reiterate again what I said, that by labeling techniques, by labeling the DNA which is just trying to open into a replication fork, people have tried to find out that particularly in the 3' to 5' direction, as there is no existence of an enzyme, they have found that there are these growth of short fragments about 1000 to 2000 base pair long, which are essentially sutured from the 5' to 3' direction, okay, and they are replicated also in the 5' to 3' direction. But then instead of doing a single base pair at a time, what happens in the 5' to 3' direction normally, in the 3' to 5' plane or the 3' to 5' portion of the fork, it is the group by group suturement of this fragment by fragment suturement which happens, and which can cause the 5' to 3' enzyme to replicate on a 3' to 5' fragment, okay, or strand or flank of the DNA. So these fragments are known as essentially Okazaki fragments, on the name of the guy who really found these fragments out first. So therefore they found out this existence of short 1000 to 2000 base pair long Okazaki fragments on the growing replication fork. Okay, so in eukaryotes this was found to be only about 100 to 200 base pairs, whereas in prokaryotes this would be as high as about 1000 to 2000 base pairs, and these fragments would then attach in bulk, okay, as fragment by fragment rather than individual base pair by base pair. This is also illustrated in this figure here. So if you see this particular example, this is the fork which is radio labeled, and this is the DNA which is radio labeled, and it is opening up as a fork, and slowly one portion is getting replicated from the 5' to 3' direction, which is perfectly okay. For the other portion getting replicated from the 3' to 5', the replication actually happens in the reverse direction, okay, it happens in the 5' to 3' direction. However, it happens through these short segments which get generated, and the segments get connected to each other rather than individual base pairs. You can see it a lot more bigger here maybe, so you can see these segments getting created, and the segments which are actually able to get sutured also in the same direction, the 5' to 3' direction, even though they are on a flank which needs to go 3 to 5, okay. So that is what Okazaki fragments are. So in a nutshell, these fragments were all polymerized in the 3 to 5', were rotated 180 degrees and to stitch the daughter strand of the fork, and the process of Okazaki fragment is slower step of the reaction, so it defines the overall reaction time as well. And so there the 5' to 3' synthesis always leads the polymerization of the other fragment. So irrespective of whatever be the case, the enzyme used is only one, which is 5' to 3', and in order to make this process a little quicker, mother nature has given this wonderful ways and means of forming a fragment and then stitching fragment by fragment rather than going individual base pair by base pair. So this is essentially a very important aspect about the DNA polymerization. Now essentially this is an engineering course. I am not going to go into the full details of the way that this enzyme would work, but then essentially we can look at enzymes really as a suturing hand, okay. You can look as if there is this kind of palm of mine which I fold like this, and then the molecules kind of pass through from one side of this palm and goes out in the other side, and this palm actually presses two strands together, and there is bonding because of that. So this is a nice analogy. Also thermodynamically this is what happens. So this can be a kind of thermodynamic map of what is going on in the reaction by looking at it as if the molecules are passing like a chain through this gap of a palm of a hand, and we are pressing this palm from time to time so that we are suturing different molecules together, okay. So using this model again, you can see the very fact. So this essentially is what the hand really looks like, this particular illustration here. Okay, you can assume as if the template strand, which is given by this yellow portion, and the primer strand, which is given by the red portion. They kind of move together, and one end of this palm, okay, from this end of this palm, and they are moving out from this other end of the palm, and you can think of as if this these are really the fingers which are kind of pressing, and this is the thumb, okay, which are kind of pressing on the molecules and developing these bonds between the base pairs. Okay, so essentially it is also a hand drawn by thermodynamic considerations. Okay, this is the way the energy would kind of be applied in order to suture the molecules to each other. So there is a very good aspect of this DNA polymerase mechanism, or this mechanism of suturement by the DNA polymerase, that it is a very high fidelity process. There is about one error which it demonstrates only in about 10 to the power 9 nucleotides. Okay, it's fantastic, because if this error rate were any different or any bigger than this, there would be severe mutations, and then we would have a continuous process of changing our outwardly physiological response, behavior, shape, size, everything else with time. But however, because of this high fidelity process, there is almost one error in 10 to the power 9 such suturements which this DNA polymerase can ever make, and that makes the process of suturement a very high fidelity, less error prone process, and then there is hardly any mutation, or a very slow rate of mutation, which happens over a considerable amount of time when subjected to certain stimuli or conditions related to the environment. Okay, so therefore the DNA replication in a nutshell is a very high fidelity process, okay, with about one error in about every 10 to the power 9 nucleotides. There are several proofreading mechanisms of the DNA polymerase which accounts for this high fidelity. Let us look at some of the mechanisms here. So the first mechanism really is where the first proofreading step is carried by the DNA polymerase just before a new nucleotide is added to the growing chain. Okay, so essentially something wherein, I think I have an illustration here, when there is a new nucleotide which is added to the growing chain, there is a proofreading step which is carried out. So this mechanism is based on the fact that after the nucleotide binding, but before the nucleotide is covalently added to the growing chain, the enzyme undergoes a conformational change. So let us say you have a moiety here which is coming, and it is about to bind to the complementary strand which is there on the template, and once it binds onto this complementary strand, it has to get attached on to this other portion of the sugar phosphate chain, right. Before this happens, the enzyme, if it feels there is a wrong binding by any chance, gives a jerk or a conformation change, and it kind of leads to cleaving this molecule away, and so in the next step the enzyme tries to pick up a different molecule and see if that is going to work or not. So before adding this portion of the input molecule to the chain, after this base pair has been bonded to the base pair here on the template, the enzyme tries to proofread and see if there is an out of shape situation, and so if there exists an out of shape situation, it suddenly changes its conformation and tries to cleave the molecule off from the growing DNA chain. So therefore there is no question of suturement of the phosphate part on this DNTP or the nucleotide to bond to the remaining part of the DNA chain. Okay. The other mechanism which is of interest is also known as the exonucleolytic proofreading mechanism, and this happens because another site, because of the presence of another site on the DNA polymerase enzyme. Okay, so the site is also called the 3' to 5' proofreading exonuclease, and it would cut off any unbonded or inappropriate bonding sites. Okay, so this is very finely illustrated here. This is the site, as you can see, This color does not work out very well. So, this is the site, as you can see, of the exonucleolytic proofreading mechanism. So, this essentially is the primer strand, this is the template strand, and they are all going into this hand like feature and going out, and so therefore, the moment here the DNA molecule or this hand senses or this enzyme senses that there is a misfitment of two base pairs along each other, it redirects the primer strand towards the exonuclease site on the enzyme, and it does not let, this is a different direction altogether, right. So, it does not let the primer portion, which is inappropriate, bond to the other template portion. So, the template portion in this case is coming from this end, and the primer portion in this case is kind of getting sutured here. So, the moment there is a difference in the base pair and it does not match up very well, the molecule kind of changes direction and goes to this exonuclease site, which causes the particular base pair, complementary base pair on the template strand to go unbonded. Okay. So, these are the two mechanisms on DNA polymerase enzyme, which leads it to kind of accurately and with high fidelity produce repeatably a whole DNA chain. So, basically that is probably all about how the DNA polymerase would try to do the proofreading and suturing of the different strands to complete the whole DNA molecule. This is of course an in vivo process, and this is done inside the cell, and that is a pathway for the daughter strands to split equally and go into the two daughter cells from a parent cell which splits up. So, after doing this, another interesting concept which is relevant for the diagnostics industry, and that is concerned with the detection of DNA, is electrophoresis. As we have already discussed before in the whole classification of electrokinetic flows, there are two different kind of flows, where in one case an external EMF is applied to cause a flow, in another case there is a pressure driven flow which causes an EMF to happen. So, in the first category, the two different processes that we discussed are electrophoresis and electroosmosis. Electroosmosis we have discussed in much details. Electrophoresis we just left with the basic definition, which is that of the motion of a charged molecule inside a medium, okay, under an electric field. So, here solid particles which may be of colloidal dimension or even larger are caused to move through static solvent under the influence of an external electric field. The velocity of the field is given by again zeta dV by 4 pi n, and where it is assumed that the thickness of the double layer is small in comparison with the size of the particle. Okay. So, we assume that there are no effects related to the double layer close to the surface, or at least there are no tangible effects of the surface double layer. The only effect that can happen is in terms of a reduced charge and an increased dia by the counterionic cloud for an ion that is moving towards a certain electron. So, here in this equation, V is the electrophoretic velocity, of course, zeta here is the zeta potential of the particle with respect to the medium, d is the dielectric constant of the medium, theta is the viscosity, and this essentially is also the applied field. Okay. This is really the applied EMF, external EMF. So, electrophoresis is done particularly for molecules like DNA, and it gives a lot of utility to find out the overall base pair numbers or size of the molecule. The way it can be done is through porous networks, comparing with the size of the DNA, a few hundred nanometers of pore sizes probably. So if you push the DNA molecule by virtue of a dragging electric field within such a sequence of pores or a network of pores, it is going to straighten up the molecule, okay. And if these pores are randomly oriented, these molecules would tend to move as a serpent within those pores towards the positive electrode, and in the process they would face a couple of different forces, which a balance between which would lead them to move in a particular direction. Of course, there is a force of attraction that the positive electrode would provide on the negatively charged DNA, and there is a force which is associated with the friction that the DNA would undergo while moving through such a set of pores or sieves. And the balance between the two forces, that is the frictional forces, probably in the backward direction is the drag force. It tries to stop the DNA or hinder the DNA from moving through this porous network, and the electric field driven force is a forward force. It is the driving force for moving the DNA. So the balance between these two really determines at what rate the DNA would move, or what would be the velocity of the DNA. So assuming that you have a bunch of different lengths that you want to separate, and you jumble them all together in a solution and try to use an electric field and inject this through this series of pores or sieves in the gel, it is almost always true that the shorter the strand is, the lesser is the frictional effect, and it starts moving faster in comparison to the longer sizes or lengths of the DNA. So therefore there is always a fractionation effect which comes into picture, with the longer ones moving slower and the shorter ones moving faster, and after a while you can see these independently. Assuming that you have intercalated some fluorescence molecules to make them visually distinct, you could see them as different bands or ladders across a DNA gel. If you can illuminate such a gel with the UV excitation frequency for the particular dye molecule. So here the following things are required. You have a separation region, as you can see in this figure here. This separation region essentially is the matrix, the sieve, the porous matrix or the porous sieve. So you put the DNA somewhere inside this matrix by making a pocket and just simple pouring, okay. So you put the DNA here somewhere, and then you apply a field wherein you make one side the cathode, another the anode, which is a positive electrode, and then dip this whole configuration in some kind of a buffer solution, an ionic buffer solution. So obviously, as you apply a voltage onto these electrodes through this external supply, there is a tendency of the negatively charged DNA to move through this gel network towards the anode of the positive charge. Essentially what it does is it gets injected into the gel material. So definitionally then, electrophoresis is really the drift of charged PCs when placed under an external electric field, and the velocity related to electrophoresis, or the electrophoretic velocity, essentially proportional to the field gradient, okay. So the applied electric field or the voltage gradient. So dV by dx, okay. Mu here is a constant of proportionality, which is essentially an estimation of the velocity per unit electric field applied, and it's a constant of proportionality between the electrophoretic velocity and the electric field. So mu equals V as dV by dx equals 1, right. So it's the velocity per unit electric field that we are talking about in terms of the mobility. So let us try to really see at a single particle level what happens, identical to what we did before in terms of electroosmosis over a particular electrode, where we tried to estimate the double layer, the diffuse layer, and then how the dynamics between the double layer, on one side it is being pulled through the externally applied perpendicular electric field, on another side it is being held back by the shear forces or the viscous forces. How the dynamics works there, we did all these things in details, Here we would try to build an identical model for a charge particle by deriving what the electrophoretic mobility of that particle will be once you take it through a medium or through some kind of an ionic fluid. Okay. So electrophoresis again is the movement of charged entities under an electric field, and also the movement of counterions, that is in electro-osmotic flows. So a couple of important things we would like to illustrate real quick here. One is that the movement of charged entities in E field where the charge is the counterionic charge. Is the electro-osmotic effect. If you remember, if there is a surface which is primarily having a negative charge, it is the counterions which would comprise the bulk flow in case of electro-osmotic flow. Here it is just the opposite, although the velocity v would still be defined as zeta d by 4 pi neta. D essentially is the dielectric constant of the medium, and I am borrowing this equation from the electro-osmosis case, because whether it is counterions or a primary ion, it really does not make much of a difference as far as the equations of motion for the charge goes. Only the charge type varies in this particular case. So neta is the viscosity of the medium. Okay. So let us now consider what will happen if an ion moves in an external electric field. All right, externally applied electric field. So the first instance that comes to our mind is Stokes' law. So you have a particle which is moving inside a fluid, so there is always going to be a drag force. Okay, let's assume the particle moves in the direction from left to right, so the drag force would essentially be in the opposite direction, and this drag force can also be found out from Stokes' law. This is a kind of frictional force that a particle faces once it flows through a medium. Okay, so it's a frictional force on any particle in a media due to viscous friction or viscous resistance. So the drag force Fr is also represented by 6 pi neta r times v. R is the radius of the particle, v is its velocity of motion. All right. Now let us suppose that the value of, let's say this is a positive charge, it goes towards the negative electrode here. So we suppose that the value of the electric field externally applied in this particular instance is given by the term x. Okay. So, if our charge here has a valency Zi, E being the electronic charge, epsilon being the electronic charge. So, the total charge on the particle here which moves is about Zie, and the total force that the particle would face in the electric field is also given by Zi epsilon x. Okay. So, the particle will only be moving in the solution if these two forces are equal, essentially causing the particle to have a uniform rectilinear motion without any acceleration or forces. Of course, there are going to be buoyancy driven forces and sedimentation forces, gravity driven forces which happen to the particles, but assuming that the particle size is small, we are talking about a bunch of different ions, we hardly get any of these effects. We can be safe as far as the gravity effects of the particles go. Okay. But then the very fact is that the drag force, only if equalized to 6 pi r neta v, if equalized to this other electrical force Fe, would create a situation where the particle would move through the solution on applying the electric field. Okay. So, 6 pi r neta v, the drag force, is also equal to the electric force which is Zie x. Okay. X is the external electric field, epsilon is the charge on one electron, and Zi is essentially the valency of the ion that we are considering in this particular example. So, v here, the velocity of the particle in the medium would be given by the term Zi E x by 6 pi r neta. Okay. So, this is just a plain case where the particle does not face any other restrictions from the counterionic cloud that it is in. Okay. However, it is of utmost importance to mention here that the particle is not alone. There is a tendency of this particle to drag a bunch of different counterions and the solution around it, and the effective charge of the particle is shielded because of the counterion cloud or the ion density which is around it. Number 2, another very important point is that the overall diameter of the particle also kind of increases notionally because of the availability of this counterionic charge. So, if we really involve the differential, the charge differential, and also the diameter differential of this particle core with an ion cloud surrounding, going through or being dragged through the solution by the external field, the equations of motion will slightly change. So, let us look at some of the aspects if we consider this particular relaxation effect. So, we call this particular effect of counterionic cloud coming and surrounding the particle of interest the electrophoretic relaxation or the relaxation effect. Okay. So, as such a particle will experience the electrophoretic and relaxation effects. We assume an effect where the particle of interest is surrounded by a diffuse double layer of charges. Okay. Now, this diffuse layer thickness is really a function of the concentration of the ions in the solution, and will go up as the concentration is more. So, higher concentrations would typically have more number of charges on the counterion cloud. So, we will kind of stop here and try to look into the whole derivational aspect of this relaxation effect on electrophoretic in our next lecture. Thank you.